Good evening. Today we are going to discuss the topic on Cayley's theorem in modern algebra. So first see the definition of Cayley's theorem. Statement: any finite group is isomorphic to a group of permutations. So here let us consider a finite group. We have to show that this group G is isomorphic to the another group of permutations. So first we construct a group of permutation. So first we take proof. Let G be a finite group and we have to show that G dash is a group of permutations. And next step we are going to prove that this G is isomorphic to G dash. So now given that G is a finite group, so therefore it has a finite number of elements, say n. Now let us take an element A in the finite group G. So let A belong to G. Now define a mapping FA from G to G, that is group to group, by FA of x is equal to AX for all x belongs to G. So where x is an element belongs to G and FA of x is defined from is mapped to AX. Here the domain group is G and the codomain group is also G. Now we are going to prove that this mapping FA is one-to-one and onto. So by the definition of onto, whenever the codomain elements are equal, the corresponding domain elements must be equal. Here FA of x and FA of y are represents the codomain elements. This is true for x comma y belongs to G. Now by the definition, FA of x will be mapped to AX and FA of y will be mapped to AY. So therefore we will get AX is equal to AY. Now since element A belongs to G and G is a group, in the group G every element has an inverse element. Therefore A will have an inverse element, namely A inverse, that is also belongs to G. So pre-multiply by A inverse on both sides, we will get A inverse AX is equal to A inverse AY. So but in a group G, the value of A inverse A is equal to identity element E. So EX equal to EY. When identity element is multiplied with any other element, we get the any other element, that is Ex is equal to X and Ey equal to Y. So finally we will get X is equal to Y. So therefore we have shown that FA of X is equal to FA of Y imply X is equal to Y. Whenever the corresponding codomain elements are equal, the corresponding domain elements are equal. So therefore FA is one-to-one. So also by the definition of onto, for every image element AX, there is a pre-image element small x belongs to G such that FA of x is equal to AX. Therefore FA is onto also. Since FA is one-to-one and onto, this FA is a bijection mapping. And also the group G has n elements. Therefore FA is a permutation of n symbols. So we can define the set G dash, which consisting of the permutations FA of the form corresponding to A belongs to G. So next we prove that this group G dash, that is the group of permutations, is a group that we are going to prove it now. Since it is a finite group, so we only to establish that the closure property only we need to check. So for that you take two permutations FA and FB belongs to G dash. Now the mapping FA is defined from G to G dash. So therefore let us take an element x belongs to G and you apply the permutation FA dot FB on x. So therefore we will get FA dot FB of x is equal to FA of FB of x, but FB of x will be mapped to Bx. So therefore FA of Bx is equal to, again by the mapping definition, it mapped to A into Bx. So but by the associative law, A into Bx can be written as AB into x. Again from the definition of permutation mapping, it will be mapped to again FAB of x. So therefore we have shown that FA dot FB of x is equal to FAB of x. Now from this we see that FA dot FB equal to FAB. So therefore again G dash is closed with respect to composition of mappings. So therefore we have shown that G dash is a group. Next we are going to prove that the finite group G is isomorphic to the group of permutations G dash. So now it is enough to we show that there is a one-to-one correspondence between the finite elements of group G and G dash. So that is we are going to show that one-to-one and onto property alone. Now let us define a mapping pi from G to G dash by pi of A is equal to FA for every A belongs to G, where A is an element of the domain set G. Now pi of A and pi of B are the elements of the codomain set G dash. So whenever pi of A equal to pi of B, by the definition pi of A is nothing but FA and pi of B is nothing but FB. So therefore FA will be equivalent to FB. So this implies FA of x is equal to FB of x for every x belongs to G. But by the definition FA of x is equal to AX and FB of x is equal to BX. Now an element this x belongs to G. So in a group G by right cancellation law, so post multiply by x inverse we get A into x inverse is equal to B into x inverse. X inverse is identity element, so therefore AE equal to BE, AE equal to B. So here also we have shown that whenever the codomain elements are equal, corresponding domain elements are equal, therefore pi is 1 to 1. Also pi is onto mapping such that pi of AB is equal to FAB. So hence we have proved that pi is 1 to 1 and onto, hence pi is an isomorphism. So hence we have established that G is isomorphic to the group of permutation G dash. Thank you.